illustrate how and what happens. But if you were to construct a quantum theory of gravity, that would be your starting point, that you would like to write down a perturbation theory, covariant perturbation theory of gravity. You will have to write down some interaction Hamiltonian. You will have to find out the corresponding Feynman rules, Feynman first order diagrams, which are just vertices. So they are free processes taking place in nature. The electron goes and it emits or absorbs photons, but it doesn't talk to anybody. This point we will just now come back to. When they talk to each other, then any two of these 8 diagrams have to combine. So if you combine according to the standard Feynman rules, you can combine any two of these 8 diagrams, and then you can construct the physical processes like electron-electron going to electron-electron, or electron-photon going to electron-photon, so Compton scattering or electron or whatever. And if you would like to construct higher order diagrams, okay, in any case, in perturbation theory, the life would not end up with 2 vertices, so you will have to go to higher orders, right? And here, by mathematical arguments, one can prove that all the contributions of the odd order terms here would identically vanish. So only even order terms contribute to physical processes and not the odd order terms. This one can prove. Okay. So then let me erase these things from here, and even this maybe now. Right. So now, out of all these 4 theories, for each theory, I would have some processes which are called as yes. Which are called as radiative corrections. Now I think we can, given these details, we can understand things a little bit better. So, radiative correction. The radiative corrections play a very crucial role in giving us the physical theories. So, vertex correction or vertex modification, photon self-energy or vacuum polarization, fermion self-energy. Okay, so electron is going or a photon is going, and here 2 fermionic lines and one line corresponding to the photon. Okay, so out of those 8 fundamental vertices, we can construct the next order diagrams, which are the tree level diagrams. So for example, or so this is electron, photon, and this is photon, electron, electron. So electron or positron, anyway. So you can very easily see that if you divide this like this, or if you divide it like this at any point, so this represents one fundamental vertex, this represents another fundamental vertex, this represents one fundamental vertex, this represents another fundamental vertex of QED, and I can combine 2 of them according to the standard rules. Standard rules, which means we can have a look at the Feynman rules. I am not going to recap them all. But for example, it's not possible that an electron is going here and it automatically becomes a tau meson or a mu meson. That's not allowed. Okay, so if Sarah is going on her bike, it always remains Sarah. Okay, it can't change to Eugenia. All right, that's the fundamental principle. Okay, so if an electron is traveling, it continues to be electron. It cannot. This is not allowed that it becomes a tau meson or a mu meson. Okay, it's not possible. All right. So these are some basic rules. One can have a look at them, and but what we need to remember here is that we can construct. These are called as the tree level diagrams. Tree level diagrams. Okay, and then you introduce some loops. So tree level diagrams do not have any loops. Okay, I cannot see any loops here, right? We cannot see any loop here. But if you were to construct, so you see on this process we have seen that now let us take example of this Compton scattering. For Compton scattering, I can introduce. So I can introduce a fermion loop here. I mean this fermion self energy here or here or here. Okay. If you do all of them at the same time, it's allowed. But then you have E square, E square, E square, e to the 6, and one IE is sitting at each vertex. One IE is sitting at each vertex. In the interaction Hamiltonian, we had seen that there was one E sitting. Maybe I had forgotten iota. So one iota times E, that is sitting at every vertex. Okay, and actually you E1 alpha beta you can level so that this photon has the level beta and this photon has the level alpha. So you can construct 3 of these, and so you can do one at a time, or so here or here, or you can do at both, no problem. But then this would be higher order diagram. Okay. So if you do it once, this is e to the power 4, iota e, and iota e. So this is e to the power 4. This is also e to the power 4. Okay, and so I can introduce this here or this here or at both. So it depends. If I take only at one, then this gives me e to the power 4. Okay. So that means I can collect in my transition amplitude sigma over n equal to 0 to infinity a of n lambda to the power n. So eventually we would write down a perturbation theory also for the string field theory. Okay, and we will see analogously what happens, how it looks like, because without that you cannot practically do anything in string theory. Okay, so you have to eventually consider some string scattering or something, of one string splitting into 2 strings or 3 strings, or the 2 strings they annihilating each other to give one string, and so on. All these things are possible, but eventually one would need to construct a perturbation theory for doing any meaningful physics. And this is the way. So this is the contribution coming from all the Feynman diagrams of the same order. So you can construct diagrams of the order e square, e to the 4, e to the 6, and so on. And as I said at the beginning, that one can mathematically prove that all the contributions originating from odd order diagrams would identically vanish. Perhaps for 1 minute you were away, I might have said this, that the contribution from odd order diagrams would always vanish. One can prove it once for all. Okay, I will skip the proof, but I think now we have a fairly good idea about what we talk about in words, blah blah blah. Okay, you read many in many textbooks on string theory, you read many review articles on string theory, and it depends. Most of the time, people they speak all these things in just words, blah blah blah, and then sometimes we get lost and we don't know what is going on. So I thought I could take a chance to illustrate a little bit further. So this actually explains us. And now let me leave the first three diagrams and let me remove all others. So now let us try to learn something out of this. Okay, some important conclusions, and I think we had left at that point because the concepts are too complicated and involved, and it sometimes needs us to recap the main points, because I want to I would be very happy that even at the end of the course you remember some basic things. Oh yes, this is the thing. Okay, and for that, because many things you can work out yourself. So as long as we are clear on all the concepts. Okay, so one important outcome of quantum field theory is that the strength of a force, which is called as the coupling constant, it depends, the strength of a force changes with distance or energy. So the strength